Thanks, Steve, for a very kind introduction, and good morning, everyone. Thank you all for coming to this very early plenary session. We have come a very long way in this community of robotics. If you go downstairs to the exhibition, it seems that quadrupeds and humanoids, they're just everywhere. And you see the same thing in the news that you get every day targeted by AI on your phones. So I had the pleasure to be part of this community for the last 15 years, developing systems that started out with this. So this was actually my, do we have an echo here, or is all good? So, good. This was during my PhD thesis when we developed the first dynamically balancing quadrupedal systems at ETH Zurich. Back then, investigating what kind of actuation we need, what the controls behind that, all model-based, and everything really curiosity-driven. So figuring out how can we make systems dynamically run. So when I was preparing for this plenary, I actually went back to my PhD defense, which happened about 12 years ago, a little more than that. And this was the motivation slide that I had back then. I said there's two reasons why we're doing all this research in legged systems. Number one is we want to make systems that can literally go anywhere. Number two is building legged systems will help us better understanding biology and biomechanics. So over the years, I got more and more attracted to this first pillar. And if you look at the image that I had then, which was a pure mock-up, and you compare that with my title slide, you realize that we're getting a step closer to this. If you have legs, you have really the advantage that you can literally go anywhere. You can get across obstacles, stairs, steps, slopes, you name it. And if you can do that, this really enables all kinds of different new businesses. It can be industrial inspection, transportation, search and rescue, whatsoever. And what you see here was a pitch deck that I was using early 2013 when I went to the first VCs and said, we should commercialize legged systems. And I got an offer, was like $500,000 for about 30 to 50% of the company. I don't remember exactly. So it's not the 50, which seems the default standard in the new world, but like 0.5. Obviously, we did not accept back then. Things changed. Things changed a lot. End of 2013, beginning of 14, Google acquired, under the lead of Andy Rubin, about 8 robotics companies that gave us the first big tailwinds to make business in this area. But for me, it was clear, if you want to make something useful with these robots, locomotion is just not sufficient. We have to make these systems autonomous. So what we started to do is integrating all kinds of perception sensing, lidars, cameras, that allow these systems to walk autonomously. And this created this Christmas tree of systems. And we were bold enough that we said, let's go and try this out in the field. So we participated in a competition which was about figuring out what kind of robots can we use for industrial inspection. This was, again, early 2014 when we had the first deployments in a trial. And it was embarrassing. These robots, they could barely walk. They were not field ready at all. We even had to bring a small ramp to get across small obstacles. So nothing was field ready. So we went back. I was starting to write grants like a mad to collect all kinds of funding that we could get to start making proper systems. Making systems that are nicely integrated. We developed first actuator modules to make robots that can walk under real-world conditions. In this case, again, tested on an industrial facility, and you see them being rain or waterproof, fall safe, etc. However, reality was, if you went to the field trip, you brought your entire equipment from your lab with you. You did surgery with the robot every day, hackathon every night, and the robots became the best friends in your bed. So if you really want to do this seriously, we said, we have to commercialize that. So we started in 2016, Robotics, where we're now about 200 people, building inspection machines. And these inspection machines happen to have legs, just because legs propel us to go across obstacles. So this is not the most dynamic robots you can think of, but you know what? in industry, people do not care too much about doing a backflip or running very fast. What these machines have to do is they have to do their job. But I would claim this is probably the most industry-ready platform that we have today. What we're trying to do with that is we're pushing this whole next revolution of robotics, which is bringing robots out of the factory floors, what you've seen in automated manufacturing, over smart warehousing, now more and more creating this autonomous industry where we have robots working in environments that are made for humans, but still doing relatively simple tasks. These robots, they're working in industrial facilities, like you can see in these pictures, offshore areas, underground areas, chemical plants. It's typically all places which is relatively hard for humans to get access or very expensive for humans to get access. And what they're doing is they're walking around, equipped with different sensing equipment, doing thermal inspection, visual inspection, acoustic inspection, they search for gas leaks and other things. And as you can see in this left video, these robots, they can be trained all in the digital world. They know where to go, they know their real-world environment from its digital environment, they know where to do inspection tasks, and then you can take these robots and directly deploy them on the real facilities. They move around, and a lot of the processing that is happening is actually happening on the machines themselves. So they try to figure out certain anomalies on the system itself, whether it's temperature anomalies, whether it's kind of visual anomalies. If they do visual inspection, they figure out where these different things are to inspect. You see in this video, like reading out the pressure meter, filing the report, and bringing that back. So in other words, these machines are kind of data collection tools on the site. You have here the dashboard where the operators sit in their room. They see whatever these machines have been collecting and are collecting. They can schedule the routines, etc. And I think that's the big work that we have to do right now. Building robots for these environments is all about reliability. We have to make systems that are properly tested on component levels, EMI, you do ingress protection. We even have versions that are ready for explosive environments, so they undergo ATEX certifications. And you do the same thing on systems level. So here you see a couple of snippets from our dojos that we have doing hundreds of stairs with extremely high reliability. Doing missions, you see on the bottom left, day and night over multiple seasons at the exact same place to make sure that your sensors work, your system work, your whole algorithms work that you're using for this kind of operations. Now, lucky for us, today we have legged robots which have just become a pure commodity. Everyone can buy them, we can try out new research, we can try out new businesses, one opportunity for all of us. But I think it's not only this. I think technology has matured so much that building such systems has become fairly easy. We can even do that in education. So these are two student projects that I want to mention, where we collected undergrad students in their bachelor for 2 semesters. We give them a vision in the beginning. In the left one is like make a magnetic climbing robot. On the right one, make a robot that can do self-reorientation in microgravity or in space. And what you see in the video is a parabola flight that we were doing with these robots. And the students, they go all the way from the idea of building that to the final prototype. They build the motor controls, they make the gearing, they make the mechatronic system, they build the codes behind that. So within 1 year, this is possible. What I want to show with that is that, like building such systems, making them walk has become fairly easy. What is still very challenging is making them do something useful. And in particular, if you think about doing something commercially useful. The other thing I want to mention here is that I think it's important that we are not stuck by trying to copy what we see in biology, but instead use our engineering skills, our possibility to just bring in new capabilities. So something that we did, and we started that in about 2018, is trying to combine this mobility that we see from the legged systems with the efficiency that we got from wheels and build quadrupedal systems on wheels. All that in the beginning, again, just curiosity driven. You have machines that suddenly can go fast, they're very efficient, that can do long-range missions, and actually it turns out they can do that without really losing versatility. So they can get across obstacles the same way as legacy systems, and actually from time to time they can do even bigger obstacles. And what is nice is that we can let these machines do something we didn't expect in the beginning. So suddenly you have new capabilities. So what I want to show with this is that I think it's important that we as engineers, we stay very creative. We can come up with all kinds of different morphologies, all kinds of different systems. I personally, I don't believe in this world where there's this one type of humanoid and this one type of quadruped. I think we're going to see all kinds of diverse morphologies in the future. And again, nice that these things are becoming commodities. You can use them, you can play around with them, and you can start new businesses with these systems. So one thing we have been doing in Zurich, and these are the people that were behind these first quadrupeds on wheels, is commercializing this for last mile delivery. The reason we're doing this is simply because typically you have to drive on roads and on sidewalks, but there's still stairs and steps that are typically in the way. So by having these combinations of legs and wheels or active suspension, you can overcome all of that, and you have now delivery services that can bring you parcels, or they can also bring you food. So next time you come to Zurich, make sure that you order food, and they are going to be delivered with these robots in certain parts of the town. Now what you have seen happening in the space of quadrupeds is what we see happening right now with humanoids, just 3-4 years later. Humanoids are becoming a commodity. We have about more than 100 companies alone here in China making robotic systems, and if you go down to the exhibition area, you're going to face this diversity of systems. And all the big guys in the world, they will tell you there's just an insanely big market with that. We're going to see billions of humanoids, and we're going to see trillion-dollar markets. Now, reality is we see massive investment, we see promising demonstrations, and we see also, and in particular here in China, it's very impressive to see a fast rate of adoption. And for sure, our community massively benefits from that. I think we have seen a tremendous acceleration in this field. However, if you're excluding entertainment, education, and maybe research as a business for a moment, there's unfortunately still not too many people that use humanoid robots commercially beneficial. So I think there's still a lot of research for all of us to be done to figure out what these robots need to do, how they do it in order to become a successful system. Now, if you're taking what I was talking about before and try to project that on this very famous Gartner hype chart, I would almost say that ICRA and IRA's exhibition is kind of a mirror of that. If you go back 3-4 years, we had everything around quadrupeds, all kinds of companies that were showing quadrupeds in these exhibitions. I think this hype is a bit over. We have understood how we built that. People start to really make it productive, and many of the companies are now going to the fairs where they really talk to the customers and not to us, to the researchers. With the humanoids, we're about here. So it also will take some time until we have this massive adoption happening. But if you ask yourself, what created this big push, this kind of Cambrian explosion that we saw in leg robots? I would say there's 3 key factors that contributed to this. Number 1, clearly, hardware. Hardware became available. We have very powerful, available actuator systems, compute systems, LiDAR sensors, camera sensors that are becoming cheap and affordable. Second thing, we saw a revolution in control. A lot of tedious, long developments in model-based controls was almost completely replaced by reinforcement learning and imitation learning. And lastly, our community got access to foundation models, which somehow help us to kind of fake some sort of a common sense in robotics. And no matter what it is, it's a super useful tool that we should use in all ways. And I'll go quickly through a couple of developments that happened in these fields in the last years. If you look at controls, we went all the way from open loop controls over simple models, templates, to model predictive control where you use the model full body dynamics, all the way to deep reinforcement learning. So what happened was that we saw an increase in model complexity from simplified models, templates, all the way to the most complex model we can think of, which you now implemented in simulation instead of in real-time optimization. And we can add on top the uncertainty and stochasticity that we typically face in the real world. So for the non-electrobotics expert in the room, I think the default standard in controls for these systems is by now reinforcement learning plus sim to real. So we train these systems in simulations. On a simple laptop like this, we can have thousands of agents. The tools are there, like the Isaac Labs of the world. You train them, you train a neural network that can use proprioceptive, exteroceptive observations and directly command the actuator commands. And we do that like in a curriculum, like in a game. The better these robots become, the harder we make the environment. And I would like to give you now kind of a firehouse version of what is the challenges, namely to bring this now from simulation to the real world. And there's a couple of contributions that our group also made in this, which I think is important to know. Number one, we realized, and this work by Jimin a number of years ago, we realized that on the one side, what we need to have is obviously randomization in your system dynamics, etc. But still, what is very important is to capture this sim to real issue is that you start to understand, you start to model your actual dynamics. And we can do that from data, collecting real world on the system, bringing that back in a simulation and getting a simulation which is way more active. So that helped us to get kind of the first policies, blind, flat ground, running in about 2018-19. Second thing is, how can we bring this now to rough terrain? In rough terrain, there's all kinds of things you have to know about friction coefficients, about damping, etc. So all of things which are super hard to simulate and super hard to use in the control. The way we were doing this is in a privileged teacher-student setup, where you essentially give a teacher any kind of information that might be useful for control, and then you let the student figure out from experience, from interacting with the environment, how to recover that information. And that allowed us to walk blind in rough terrain. Number three, you have to figure out in how you can incorporate perception. For everybody who does perception in robotics, they understand perception is very bad. It can be that you're walking through vegetation, you're going to walk through snow. So what you're seeing is just not what you're feeling. So the question here is, how can we balance the two? How can we merge exteroception, proprioception, and let the robot itself decide how much can I rely on what I see versus how much should I rely on what I feel? And these are the controllers that we are using in all kinds of different deployments. We see in the left video a couple of hikes that we were doing with a person remotely control that. On the right-hand side is a DARPA subterranean competition where we had these kind of policies running on all these robots doing underground exploration in caves, networks, and urban infrastructure. The fourth element was, how can we do now more complex maneuvers? So think about the problem of bringing this robot on this box. So the way we did this, we moved away from velocity tracking to position commands. So all you're doing is you tell the robot you have that goal position somewhere, and you have a certain amount of time to go there, and you let it figure out by itself what to do. And that's what the robot is doing. You see it goes there, it probes, it prepares, and it pushes itself up. There's also some tricks you have to do with the perception. I'll come to that in a minute, in how you extrapolate in what you're seeing. But to me, these behaviors, they look pretty natural. And all these behaviors, like using the legs, using the main body, it was super hard or impossible to achieve using model-based approaches. They're all dynamic, so change your environment, and the robot will just keep trying to do it. It's not only that you can jump on things, you can also jump down, you can cross gaps, you can go underneath, so all kinds of different behaviors. So you learn these different skills with the robot. I can even do more complex things, like here is a skill of climbing ladders. And these skills, they're all, again, robust. So you go there, you disturb the robot, and it'll figure out a way to still kind of achieve what they're supposed to be achieving. And as I mentioned before, it's always important that we incorporate directly perception into this in order to make them also operate outdoors in the real world, where perception might not be perfect. Now, when you have all these skills, the next big step is how can you bring all of that together? And this was work that we published this year, where we essentially take these individual tasks. In a second step, you go and you distill all of that into a single policy, and you go to new worlds, you refine that, and if you have something that you haven't observed before, a completely new task, you learn that and you add that into your task space. So by doing that, it kind of generalizes. So we can have single policy that get across all these individual objects that we have been facing in the world before, and it's actually getting better than the individual skills, so there is some learning from each other. And the very nice thing is that it kind of scales or generalizes to new things. So here's a robot crossing real-world scenarios in a search and rescue training camp. We're going every year with the whole team and a lot of friends, the whole field robotics community of Switzerland. We do a 1-week trial period where we go to this type of infrastructure. And if I look back like 5-6 years, it was not to be imagined that we could ever send robots just up there by telling the robot, like, go on this pile of collapsed building, and I think we are there right now. Even if it's slippery, these robots will somehow manage to do that. So I think it's fair to kind of extrapolate a little bit. If there's just a little bit of this trend continuing in how we're improving mobility of these systems, there's no doubt, A, that mobility is good enough to do something with these robots that is useful for us, and B, that we get to a level where this mobility is achieving almost what certain humans or certain animals can do. Not everyone, of course. What I think also is nice is that although this is not perfect, it fails, but it fails in a very graceful way. So here the robot tries to get across this car. It just doesn't manage to get across this car. But it doesn't freak out, and you don't have to go and rescue it and like restart it and whatsoever, but it just like it realizes, I can't do this. And I think that's a very important thing. Now the people behind this was Nikita and David, Julian and others. They essentially took this technology, created flexion robotics, where we are taking the same kind of technology and apply that in extended version to humanoids, which are a little more complex. Now, obviously, one thing you can do is this kind of standard pony tricks of standing up and then moving around. But what I think is much more important is that you can incorporate now this perception of the real world and make robots that can cross all kinds of different environments. And they do that in a very gentle way. So you see here a couple of pallets which are challenging to see. You have gaps and things like that in between. And these robots will just smoothly walk across that with a very high reliability by now. Here's a stair. Also this stair, if you look at that, it looks boring. And I think that's where we have to be. We have to have robots that look boring, and as soon as they look boring, they become very useful for applications. There's one big benefit that we're having with humanoids. Humanoids just look like humans, and by looking like humans, that helps us that we can also take data from humans in order to make the systems move like humans. And I'm going to show you in a minute in how this is happening. So here are some more experiments, like getting across environments where you see all the disturbances, and the way these systems react is already in a pretty beautiful way, I would say. Now, what you can do in order to inject this human data is that you start from either like collecting by video, collecting a motion capture, or take a motion synthesis approach in order to generate these tasks that you have to achieve. You then retarget that on your structure that you have from the humanoid and use that in order to learn the policies to execute that. So this simplifies all these reward function tunings that you're having on these robots before you then go and deploy that on the actual physical system. Now, one thing that is missing in here is that this is all kind of deployment in known worlds. It's nothing where the robot really has to see, understand the environment from the perception point of view. And I want to show one work that we recently published, which I think has a lot of potential in kind of combining what we see with what we feel in order to make these robots move across challenging ground. So we are developing here an encoder mechanism that looks at the height maps that we have of the environment, at the perception, at the proprioception, and what it does through an attention mechanism, we train this robot to pay attention to the right features in its world in order to make it walk, in this case, across sparse footholds. And obviously, you can do the same thing also for your hands, for climbing maneuvers, etc. So you get a machine that allows you to get across obstacles, stepping stones. Even if this world is kind of moving around, you have reactive behaviors. And these behaviors, from time to time, they're very special. So you see here slipping, the robot reacts and uses the other foot in order to compensate. But it understands that it has to step on this thing because that's where it has to pay attention before. Now, I hope that with these examples, I could show you that in locomotion control, we went a long way from like very complex, very structured, classical model-based control to something which is much more a simple neural network that runs on these systems, where we don't have a lot of heuristics, where we don't have a lot of simplifications, a fully learned pipeline. But I also said that locomotion itself is not sufficient. We need to make robots that are autonomous. And if you look at the whole stack, and this is by far, it's not complete at all, but it shows you all the different elements that are needed, from state estimation over environment mapping, terrain mapping, to cost function estimation. All of these modularized systems with a lot of heuristics in there, all of them running at different loop rates, creating delays. So it's pretty hard to make a running system with that, and pretty hard to make a very fast running system with that. So if you see what's happening in controls, we probably will see the same thing happening also with this autonomy layer, that we have things coming much closer, locomotion and navigation being integrated into each other, whether it's hierarchically learned or jointly learned, doesn't really matter. No explicit state estimators, no explicit terrain cost maps. We can use VLMs or LLMs for like task scheduling, for this whole reasoning or semantic reasoning. And I will not elaborate too much on this, but I would like to show you a couple of examples in how we're using these types of pipeline. So here is one very recent work that was actually accepted for publications 3 days ago, work by Fan, who's also sitting here in this room, where we essentially start first with pre-training an image encoder that captures kind of the spatial features at different scales. And we do that using tartan ground, but you can also use other kinds of data sets that are out there. Then you train attention mechanisms in order to compress and emphasize on the right features in your environment. And then the last element, and I think this is the big innovation in here, is that you add a spatially enhanced recurrent unit, which really learns the spatial transformation, not only the temporal dependencies, and allows you to remember what this robot has seen in the past. So what this does is essentially you have, over time, if you look at the features and how they have been in space and time, you can remember these features. And it allows you to do completely mapless navigation. So you see here training and simulation, where you have these robots going around all kinds of different environments, different types of environments. You see on the top left a maze, where the robot enters this maze, figures out it's a dead end, remembers there was openings, goes back, and explores to other directions. So if you take this and deploy that on the actual system, you get behaviors like this. So this is our very cluttered office space, and we tell the robot, go to the other side of the office space. It'll go there, try to navigate there. You see in the top left video where the robot pays attention to in its environment, figures out there's a dead end, tries a new way, again dead end, goes back again, and tries out a new way. So we have this exploration kind of integrated in this whole navigation pipeline without having any explicit mapping. And that allows us to go fast in challenging environments like you can see here in the forest, where again you tell the robot, like, go to the other side of the forest. And it understands that it has to pay attention even to thin structures, thin objects, thin obstacles in your environment, and navigate around that. So if you go and hike with these machines, it actually turns out that it's pretty hard to catch up with them. They're getting very good in doing this. Now, if you have all of these skills, I would like to come back to my very start image that I had. So this original problem of us doing a hike, you remember I had the goal to go to that peak over there. Now what you would do is you would never go shortest path. For us, it's very clear if I want to go there, I actually look up my hike map and I figure out roughly where I have to go. Then I see this road in front of me. I'll just follow that road until it brings me to the next road, and then I can climb up there. That's very intuitive. But the question is, how do we bring this intuition into robotics? So the way we are doing is that we're looking at kind of the image that this robot sees, and we're then just asking a VLM, in this case it was GPT, like, what do I see? What is the risk of this terrain that I see in front of me? Where should I walk through? And this GPT analyzes the world that I see around me, and it can do some risk associations. If you ask it where to go, it will not tell you the right solution, but if you ask it, like, what is the right terrain that I can walk on, it will tell you the right semantics for that. And that allows you, in order to get semantics into the game, and use that in combination to what I've shown you before with kind of the geometric navigation. So you can take the semantics, you can merge that with your geometry, and now you have semantic-based navigation. So if you take that, you can start doing bigger tours. We're not ready to go to the Matterhorn yet, but we can do the tourist hikes, which are on the other side, on the Gornergrat. So what you would do if you want to do a very long-term hike here, so this is a 10-kilometer hike that we did with these robots, is you would start with a hiking map or a satellite image where you figure out, like, where is about the way that I have to navigate with my robot. This gives me kind of sparse waypoints that I can tell the robot where the main directions are, and then you let the robot kind of follow that. These robots are following this roughly. They look at their local environment and then locally decide, depending on what they see, depending on their skills, and where they should walk through. Here the example, like walking around this lake, you see how the lake is classified as super dangerous, never go there. You have the road, which is your main way, where you should walk. So even if your GPS coordinate tells you should jump in the lake, you can obviously take your semantics and let the robot follow that. Here, some railroads on the side, which you should not hit with the robot, and just go through it. Now, it's not perfect yet, but I think it goes into the direction where we're going to see this ubiquitous autonomy with these robots. And if you can make them autonomous for these kind of environments, we can also make them potentially autonomous for other types of environments. This is work that we were doing with a couple of colleagues from Italy, where we are deploying these robots on Etna for a simulated Mars or Moon mission. The robot is going into the craters, measuring plumes there, doing a big autonomous mission. And the reason we're doing this is because at some point, I believe that we should have these robots, like being also the robots, the rovers of the future, going to Mars or a Moon. And we actually have a big project that we started. So if there's any space enthusiasts in this room who want to work with that, or any people that have too much money that they have to place somewhere in a fancy idea, come talk to me afterwards. So the goal is, like, can we have Legate systems explore lava tubes on Moon? Now, before I come to the end of my presentation, I would like to spend 5 minutes talking about something slightly different. And that's because of a lot of discussions I had during this week with kind of the young generation of researchers that are here. So to me, it feels kind of this pressure that, like, everything is about humanoids today. We have this big wave. The exhibition is full of them. We have all the big pioneers out there that tell us humanoids will solve everything. So I think there's a danger that we kind of forget about all the other cool, extremely relevant, and very impactful domains where we can apply our research. So something we have been doing in my group for the last 10 years is, like, applying this to excavators. It's a very complex robot, many degrees of freedom, super complex manipulation problem. You're interacting with heterogeneous ground. You have a machine that has very complex actuation dynamics, many degrees of freedom. So it's exactly the same problem as for a humanoid. And there's millions of them already out there, not automated. So what we're doing is we're taking the same technology. We let the robot move around. We learn the actuator dynamics, and then we go and we fuse that with reinforcement learning-based simulation. And then we train these robots to do whatever they have to do in the real world. This can be grading tasks, this can be like moving tasks, this can be digging tasks in all kinds of different terrains, even if it's hard or if there's boulders underneath. And the students behind this, they also saw this opportunity of, we should take this and we should actually make a company out of it. So they created Gravis Robotics, where we are turning earth construction machine into robots by adding a roof rack with all the compute, sensors, everything. That's kind of the brain of the humanoid. You plug into the machine control, you have all this GPS, GNSS, and perception on it, so the robots perfectly see their environment. You give the human operator a simple way how it can command these robots, can be loading something, can be do a completely foundation work, whatsoever. And these machines are becoming pretty capable. You see here some precise earthwork. You see in the second column building rock walls. So these are unstructured objects, 2-ton heavy, that you assemble in a complex 3D structure. I would say it's a very complex manipulation problem, but just at very, very large scale. So every single object here is about 2 tons heavy. And then on the far right, you see a completely autonomous foundation that these robots are doing, like from the beginning to the end over multiple hours, digging this out. And if this was not convincing enough, I would like to stop with a last video where we have this small skid steer, which I think is a very funny vehicle. What you're doing with this machine is, again, we are moving it forth and back. We let it learn its internal dynamics, which is super challenging. I don't know how to model that from first principles. And then you let simulation explore to do something with it, and I hope sound is on now, so you get this last video. It's a lot of fun to sit in there if you do this. So I hope with this last video, everyone is awake again and ready for an exciting conference day. And also hope that some of the young talents start thinking about all the exciting opportunities that are out there for robotics and for learning. There's much more than just humanoids. Thanks a lot.